Let's use harmonic oscillators to investigate the Lagrangian and Hamiltonian formalisms in classical mechanics. In the previous video in the quantum mechanics playlist, I introduced the Lagrangian and Hamiltonian formalisms when I was talking about Poisson brackets. In that video, the focus was comparing Poisson brackets in classical mechanics and commutators in quantum mechanics. And we saw that there was a neat translation from classical mechanics to quantum mechanics. What we're also going to see is that the harmonic oscillator and the language of Lagrangians and Hamiltonians translate very well from classical mechanics to quantum mechanics. But this video is just going to focus on the classical mechanics. We're just going to try and understand the Lagrangian and Hamiltonian formalisms using the example of a simple harmonic oscillator. So let's begin by writing down the Lagrangian. For a simple example, like the harmonic oscillator, what we're going to have is a Lagrangian of the form where we have the kinetic energy minus the potential energy. So I'll write that down over here. Fancy L is going to denote the Lagrangian, and the Lagrangian depends on the position coordinate and the time derivative of the position coordinate, which we can also call the velocity. This dot notation is Newton's dot notation. It is shorthand for dx dt. So this is the same as velocity. But we want to write it in this form because in general, we might not be talking about position. This coordinate could be a generalized coordinate. And in the language of Lagrangian and Hamiltonian mechanics, we want to use generalized coordinates. So we generalize the concepts from Newtonian mechanics and we use all of these mathematical abstractions, and they give us the equations of motion in a very elegant way. So let's write down the Lagrangian. The Lagrangian is the kinetic energy minus the potential energy. So we're going to have a kinetic energy term that's 1/2 mv squared, but v is the velocity, which is x dot. So I'll write it in this form, x dot squared. Then the potential energy, I'm going to write as m omega squared over 2. And so this is a little square up here. And then we have x squared. So m omega squared can be rewritten as k. You can have k over here. And that comes from the convention of Hooke's law. And we'll talk about Hooke's law when we get to the equations of motion. So the important thing to notice is that this is a kinetic energy term and this is a potential energy term. This kinetic energy term depends on how fast the particle is moving. And this potential energy term depends on where the particle is. Potential energy is determined by your location, and the kinetic energy is determined by your velocity, how fast you're moving. Velocity is a very useful coordinate to use, or a very useful variable to use in Lagrangian mechanics. But when we go over to Hamiltonian mechanics, we're also going to want to talk about momentum. And in fact, position and momentum have very deep connections, especially in quantum mechanics. So let's have a look at how we can get momentum from this Lagrangian. The momentum P is equal to the partial derivative of the Lagrangian with respect to x dot. So this x dot is the same as this velocity that we're talking about over here. And this is called the canonically conjugate coordinate. So momentum and position have that special relationship. So let's evaluate this partial derivative. So this partial derivative is going to be with respect to x dot. There is no x dot appearing in this potential energy term. There's only an x dot in the kinetic energy term. So we can use the power rule for differentiation, and that's going to get rid of this 2, and it's going to cancel with this half. So that's equal to mx dot. Now we have momentum is mass times velocity. That is what we're used to from Newtonian mechanics. But this is not always true in general. Momentum can be some very complicated function of coordinates and different constants. It doesn't even have to have the same units as momentum. That's what happens when we generalize in Lagrangian mechanics. This coordinate doesn't even have to have the same units as position. But in this case, because we're talking about this familiar example of the simple harmonic oscillator, these guys do have the same units and they are the same quantities that we use to describe the harmonic oscillator in Newtonian mechanics. Now, let's use the Euler-Lagrange equations, which are essential in Lagrangian mechanics, to find the equations of motion. So I'll do that over here. So first of all, we're going to have to take the time derivative of this quantity, of this momentum. So we have the partial derivative of the Lagrangian with respect to x dot. That is equal to the time derivative of this over here. We're just taking the time derivative of this momentum. So all we have to do is differentiate this term. And that's going to give us mx double dot. And x double dot is the same as the acceleration. We've got the second derivative with respect to time of position. So we've gone from velocity to acceleration. And this mass is just a constant. It's not affected by the time derivative. This is just one half of the Euler-Lagrange equation. We have another half, and that's this. We have a partial derivative of the Lagrangian with respect to x, so with respect to the coordinate. So the Euler-Lagrange equation tells us that this is equal to this. So what is this when we evaluate it? What is the derivative of the Lagrangian with respect to x? Is there an x appearing in the kinetic energy term? There is an x dot, but x dot is an independent variable. We're treating the position and the velocity as these independent variables. So when we differentiate, this is just going to give 0. We're only going to get a non-zero contribution from this term. And again, we're going to use the power rule for differentiation. This 2 is going to come down, and it's going to cancel this half. So this is going to be equal to minus m omega squared x. So this is what we've got. We've used the Euler-Lagrange equation, and we've got this relationship. Notice that m is present in both of these terms, so we can cancel m off of both sides of the equation. And that's going to give us this equation of motion. X double dot is equal to minus omega squared x. So this just comes from canceling the mass. So all we've done is written down the Lagrangian, kinetic minus potential. Then we found the equations of motion from the Euler-Lagrange equation. And that is the toolkit that Lagrangian mechanics gives us. This is all in the Lagrangian formalism. So now we have an equation of motion, but we don't have the solution yet. We don't have the trajectory. To find the trajectory of a particle, what you have to do is solve the equation of motion. And this equation of motion is a second-order differential equation. What function would satisfy this? So what function x of t would satisfy this? We need a function that, if you take the second derivative, gives you back the same function with a minus sign. And can you think of some elementary functions that satisfy that? Cosines and sines. So cosines and sines would be a solution of this. And the general solution would be a linear combination of cosines and sines. And the arguments of the cosines and sines would be omega t. So omega t inside of the cosines and sines, if you add those up together with some coefficients, that's going to give you the general solution. And you're going to need some initial conditions to solve this. You need to know the position at the initial time, and you also need to know the momentum, or in other words, the velocity. If you specify the velocity, you also know the momentum. Or if you specify the momentum, you know the velocity, because of this relationship over here. So that's in general true in Newtonian mechanics as well. When we have F equals ma, force equals mass times acceleration, if we have some expression, some function for the force, we're just linking that to mass times the second time derivative of the coordinate. So F equals ma also gives us a second order differential equation to solve. And we need two initial conditions. We need to know the position and the velocity at t equals 0, or at t equals the initial time. So that's essential. That's one of those unavoidable properties of ordinary differential equations, especially when they are second order differential equations. So you can't solve this if you don't have the initial conditions. So that is the procedure for the Lagrangian formalism. You write down the Lagrangian, you apply the Euler-Lagrange equation, and then you get the equations of motion. After you have the equations of motion, you put in initial conditions and you solve the equations of motion, and that gives you the trajectory of the particle. So this is just a one-dimensional example. We can also have higher dimensional examples. So now let's go from the Lagrangian formalism to the Hamiltonian formalism. So let me write this underneath. The Hamiltonian formalism we can get from the Lagrangian formalism. All we have to do is we have to take the Legendre transformation. The Legendre transformation is going to make a Hamiltonian out of this. So if we have h is going to depend on x, and it's not going to depend on x dot, it's going to depend on p. We want to write this Hamiltonian in terms of the momentum, which is canonically conjugate to the position. That is the terminology that is used. Canonically conjugate. That's because we're doing a Legendre transformation. So this Legendre transformation is only going to have one term, and we're going to have p times x dot. So P times x dot over here. And then we're going to subtract off the Lagrangian. And that Lagrangian depends on x and x dot. So this is the Legendre transformation. And you may have seen this in thermodynamics as well, where we want to go from one potential to another potential. And we want to write those potentials in terms of convenient coordinates. So in Lagrangian mechanics, it is convenient to look at the positions and the velocities, or the dots, right, the x dots. But in Hamiltonian mechanics, we want the positions and the momentum. So we have these canonically conjugate variables. So this is the general form that's going to work for any one-dimensional system. But now let's actually substitute this Lagrangian and this momentum that we have. What is P times x dot going to be? So P times x dot is going to be equal to, first we have this mx dot, that's P, and then we have an extra factor of x dot. So we're going to have mx dot squared. In general, if there was more than x, if we had x, y, z, and other coordinates, we'd have to take a sum over here. And for each of those coordinates, we would have a canonically conjugate momentum. We'd multiply those guys together. We'd have the coordinate dot with a time derivative of the coordinate times the momentum. We'd sum that over, and then we would subtract the Lagrangian. That's in the discrete case. But if we had a continuous case, like in field theory, then that sum would turn into an integral, because summation turns into integration when we go from discrete to continuous. So here we have mx dot squared. That's this term. We still have to subtract the Lagrangian. So let's subtract this Lagrangian. This kinetic energy term is going to get a minus sign. So we have m on 2 x dot squared. And what's going to happen to this? Well, we're subtracting, so we're going to have minus times minus, which is going to give a plus. So now we have plus m omega squared over 2 times x squared. So that's very interesting. If we combine these guys together, we're going to have a whole minus a half. So we have a whole minus a half, and that's going to give us a half. So what we're going to get is just kinetic plus potential. But what I want to do is actually, I want to write this in a slightly different form. First I'll evaluate that step. I'll write that over here. So we have m on 2 x dot squared plus this potential energy term, m omega squared on 2 x squared. But this is actually equal to, we can write this kinetic energy term in terms of momentum. So we can have p squared over 2m. And then we're going to add to that m omega squared over 2 x squared. Now we have the Hamiltonian for the simple harmonic oscillator. And this is familiar when we were talking about in quantum mechanics. We had this same form, but instead of p and x being classical variables, they were operators in quantum mechanics. So here we are, we've recovered the Hamiltonian. We've turned this Lagrangian into a Hamiltonian by using the Legendre transformation. So that's what this magic term does over here. And by subtracting, we've turned that potential energy from a minus to a plus. And this combination over here has just given us this kinetic energy term. So that is essential. So the way we went from this step to this step is using this blue relationship over here, P equals mx dot. Now, I quickly want to show you what you can do with Hamiltonian mechanics. With Hamiltonian mechanics, or in the Hamiltonian formalism, you can find x dot. What is x dot? Well, x dot is the Poisson bracket of x with the Hamiltonian. And that's the same as the partial derivative of the Hamiltonian with respect to momentum. And what's that going to be? We have to do the partial derivative with respect to momentum. We have p squared over 2m. We can use the power rule again. That's going to give p over m. And so what is this telling us? This is telling us that momentum is mass times velocity. This encodes the same information that we have up here with this canonically conjugate variable. So the Lagrangian and the Hamiltonian are encoding the same physical information. Now let's have a look. So this is x dot. We've got the time evolution of x by taking the Poisson bracket with the Hamiltonian. Now let's do the analogous thing for momentum. For momentum, we have the Poisson bracket of p with h, and that's equal to minus the partial derivative of the Hamiltonian with respect to x. And what is that going to give us? Well, we again have a similar situation over here. So we're just going to get minus m omega squared. This 2 is going to cancel with the half when we use the power rule for differentiation, and then we have an x. And what is this telling us? The time derivative of momentum, that is force. So this over here, this is force, and this is displacement. This is the position. And this is just a constant. We can repackage m omega squared as k. And we can actually write down Hooke's law. Force is minus kx. So m omega squared is exactly the same as k. It is that spring constant if we're dealing with a spring. That's a type of simple harmonic oscillator you will encounter in nature. This is a physical system. So you can see that in Hamiltonian mechanics, we have two first-order differential equations. That's these ones over here. We're just taking one derivative. And in Lagrangian mechanics, we have a second-order differential equation. And we've recovered a lot of the concepts from Newtonian mechanics. We've recovered this relationship between momentum and velocity, and we've also recovered this force relationship over here. This is Hooke's law. So it's a very, very important relationship that we've recovered. Now let's have a look at a similar example. This is a very similar system. So I'm going to write another Lagrangian that has a very similar form to this. So this Lagrangian is going to depend on the magnetic flux and also on the time derivative of the magnetic flux. And instead of x, I'm going to use this capital phi. So this is magnetic flux. It does not have units of position. It has units of magnetic flux. So it's a completely different quantity, but it's going to have the same behavior as position. It's going to behave like a generalized coordinate. So let me write down this Lagrangian. Here we have C. C is the capacitance. And C is actually going to play a similar role to mass. So we can map this mass to capacitance. And what about the potential energy term? Well, the potential energy term is going to have this flux squared over 2L. This L is the inductance. So this Lagrangian is actually describing a circuit. It's describing a circuit that has a capacitor and an inductor. And the energy is being transferred around in between the capacitor and the inductor. In the same way that the energy in this simple harmonic oscillator was transferred between kinetic and potential. We're going between kinetic and potential, and here we're going between the capacitive energy and this inductive energy. So L plays the same role as this K. Well, actually, it's 1 over L. So taking the reciprocal of L, that plays the same role as this K. And K is equal to m omega squared. So you can actually use this capacitance and this inductance to define omega, and particularly omega squared. And we'll see that when we get the equation of motion. So let's find the canonically conjugate variable. So what is the equivalent of momentum? It's not going to be P, it's not going to be momentum, but it's actually going to be charge. So charge is actually going to have those properties. Charge is going to be the partial derivative of the Lagrangian with respect to the time derivative of the flux, this phi dot. So phi dot is over here, and that is analogous to this form. We're taking the canonically conjugate variable. So what is this giving us? This is going to give us an analogous expression. We just differentiate with respect to phi dot. Again, we use the power rule for differentiation, and that gives us the capacitance times this phi with a dot. So all we've done is we've gotten rid of this quadratic. This 2 has come down, and it's cancelled with the 1/2. And this is going to play the role of momentum. So it's non-momentum. It doesn't have the same units of momentum. It actually has the units of charge. What we've got is charge over here. But charge is going to act just like momentum acts in these equations. So let's apply the Euler-Lagrange equations. And I'll do that underneath. So the Euler-Lagrange equations are going to have exactly the same form. We're going to have to take the time derivative of this canonically conjugate version of this flux. So we're going to have phi dot over here. And that's going to be equal to the time derivative of this, and that's just capacitance times the second time derivative of flux. So you can see this is analogous to this. This is analogous to ma, or mass times acceleration. What we have over here is mass times acceleration, but instead of mass and acceleration, we have capacitance, and we have the second time derivative of magnetic flux. And what is this equal to? Well, this is equal to, from the Euler-Lagrange equations, we have a partial derivative of the Lagrangian with respect to this magnetic flux. And what about this? So this comes from the Euler-Lagrange equation. This and this are equal by the Euler-Lagrange equation. How are we going to get this? Well, all we have to do is differentiate with respect to the magnetic flux. That's going to give minus this magnetic flux over the inductance L. So this is a quadratic polynomial. We use the power rule for differentiation. It gets rid of this 1/2. Those 2's cancel. And we're just left with this. So now we actually have an equation of motion. I'll write that equation of motion down over here. So what we have is, I'll take this c to the other side, we have the magnetic flux differentiated twice with respect to time is equal to itself with a minus sign. We have minus the flux over, I'll bring this capacitance down here to join the inductance, over LC. So I'm just dividing both sides by capacitance. I divided both sides by mass over here when I was simplifying this equation, but now what I'm doing is dividing by capacitance. And these guys come together. So what is this combination LC? This combination LC is playing a very similar role to this omega squared. So we have a minus sign over here, and we have a constant. So we can actually make a mapping between these guys, and we can say this omega squared is playing the same role as 1 over LC. Or in other words, we can say that omega is the same as 1 over the square root of LC. So by tuning the inductance and the capacitance of this circuit, we can make this angular frequency what we want it to be. So we can choose an angular frequency based on the inductance and the capacitance of this circuit, of this LC circuit. This is called an LC circuit because it has an inductor and a capacitor. And L and C are the standard notation for those quantities. So you can see this correspondence. This is actually the same ordinary differential equation. We just have a different variable. Over here we have magnetic flux, and over here we have position. And this LC actually plays the same role as this omega squared. We just have to find this correspondence between these variables. So this gives you the characteristic time of oscillations. So it's a very important quantity. Now let's take the Legendre transform, and the Legendre transform is going to give us the Hamiltonian. So I'll write that underneath here. So the Hamiltonian is going to depend on the magnetic flux, and it's also going to depend on the conjugate variable, the canonically conjugate variable, which is charge. It's not momentum, it's charge. And that's going to be Q times the time derivative of the flux, phi dot, minus the Lagrangian. And the Lagrangian has this term with the flux, and it also has this dependence over here. So what is that going to give us? Well, that's going to give us a very analogous form to what we have up here. So I'll substitute all of this in. So what we're going to get is Q, well, actually this Q, if we substitute it in, is going to get C. So we're going to get C, then we have the flux, time derivative of the flux, all squared. And then when we subtract off this Lagrangian, we're going to have C on 2 times this time derivative of the flux. And then this minus is going to turn to a plus. And have a look at what we have over here. We still have that potential energy, but it's changed sign. And now we can write this in an analogous form. We can write this as kinetic plus potential. But what I'm actually going to do is I'm going to write this in terms of Q. And that's going to give me this. I'm going to have Q squared on 2C plus this magnetic flux squared on 2L. So they have a symmetric relationship. Charge and flux have a symmetric relationship over here. So all I've done to go from here to here is I've combined these two terms together. This is a whole minus a half. That gives me C on 2 times this phi dot squared. And then I've substituted this relationship here for Q, and I've solved for Q, and all I have to do is divide by this capacitance. So that is analogous to what we have over here. We have P squared over 2m. So we've gone from this form to this form. We've gone from velocity to momentum. And over here, we went from this phi dot to charge. So this is the Hamiltonian. And finally, we can use Hamilton's equations. And we can find what the time derivative of the flux is. The time derivative of the flux is given by the partial derivative of the Hamiltonian with respect to the charge. This is playing the role of the momentum. That's what we have up here. And all we have to do is differentiate this guy, and that's going to give us Q over C. That's what we have from this equation. And what about the other variable of interest, which is Q? Well, Q dot is going to be minus, so this is analogous to this equation over here, is going to be minus the partial derivative of the Hamiltonian with respect to this flux. So we have flux over here. And it's going to actually give us this term differentiated. So we're going to have minus this flux over the inductance. So this is Hamilton's equations. We've used Hamilton's equations using these generalized coordinates. So we have magnetic flux, and we also have charge. So here we have the time derivative of flux. It's proportional to this Q. And we also have the time derivative of charge, and that's proportional to minus this flux. And this inductance and capacitance, they're just constants that are along for the ride. So both of these guys have the same mathematical behavior. All we're doing is rewriting constants. The variables are behaving in exactly the same ways. They don't have the same physical units. They don't have the same physical dimensions, but they have the same mathematical behavior in Lagrangian and Hamiltonian formalisms. The important thing to remember is that in Hamiltonian mechanics, you can actually you can draw phase space representations. And if you set this Hamiltonian over here and this Hamiltonian as well equal to some constant, you can draw contours of constant energy. And if you set this into equal to a constant, then what you're going to get is an ellipse. You're going to get elliptic contours. And these elliptic contours are going to correspond to constant energy. And so if you're at the origin, you're going to have x equal to 0 and p equal to 0 over here. You're not going to be moving at all. But as soon as you move away from the origin, you're going to sit on ellipses. And those ellipses are all going to have constant energy. And you can find the intercepts into the axes of x and p by setting either p equal to 0 or x equal to 0. And we'll have a look at phase space diagrams and how they translate into quantum mechanics as well in later videos. So in this video, we've seen the Lagrangian and Hamiltonian formalisms, and we've investigated them with an example. And that example is the simple harmonic oscillator. And then we looked at an analogous example that deals with circuits. It deals with circuits that have a capacitor and an inductor. So that is what we've discovered in this video. For more videos like this, make sure to click on this over here. You can find more videos in the Quantum Mechanics playlist.